So hi, everybody. My name is Michael Peth. I'm a grad student at Johns Hopkins, working with Jennifer Lotz, and also working with Peter Freeman from Carnegie Mellon, and also at Hopkins and Space Telescope is Ali Reza and Greg Snyder. So I feel a bit of an outlier because my thing has nothing to do with modeling or anything. But so it's called it's the PCA classification of CANDELS non-parametric galaxy morphologies. So I'll get into really what I'm talking about. So motivation, I probably don't have to tell everyone here that there's processes that grow and quench galaxies, and these processes are different for ellipticals, spirals, and irregular galaxies. But how can we really determine what an elliptical, spiral, or a regular galaxy is? There's lots of different ways that we could do it. Traditionally, you could just visually classify them as a disk, a spheroid, or irregular. But sometimes this can lead to us missing rare and subtle features in this kind of classification that would be really helpful for characterizing evolution of galaxies. So how we go about doing this is quantitatively with non-parametric morphologies, and the traditional ones that people have used many years, concentration, asymmetry, the Gini coefficient, and M20. And in addition to 3 newer statistics, which were developed only a year ago. And these include, so these were developed by Peter Freeman et al. In 2013, and the first of which is called Multimode. And this measures the ratio and size of pixels of the 2 brightest regions, or clumps, if you will. So this diagram here shows a galaxy, and it's outlined by what we would say is the galaxy from its segmentation map. And on the right, this same galaxy is outlined by the regions that this M statistic would say are the brightest region and the second brightest region. So based on the sizes of these, it determines what multimode is. So a multimode is a good way of determining 2 bright knots and can show merger remnants. Then there's also intensity, which is the ratio of flux in these 2 brightest regions. So it goes hand in hand with the M statistic, and they're similar. And lastly, there is deviation statistic, which measures the distance between the center of the brightest region of the galaxy and the intensity centroid of this galaxy. So in this galaxy here, the intensity centroid is where this green circle is, but the brightest region is actually where this white X is. So we see that there's actually quite a difference in the deviation, and it tells us that this galaxy is pretty irregular. So so now that we know what we even measured, what do we do with them? And so I used a principal component analysis on these 7 morphology parameters, specifically for CANDELS UDS galaxies, and we only focused on a certain redshift range around Z of 1.5, so that we could get a specific rest frame band. And we only chose high mass galaxies that were also bright. So I have to mention that there was a study using PCA of galaxy morphologies, the ZEST study by Scarlata et al., and some of the authors are here, so I just say that it was a good paper, so not just because they're here. But this was different because they covered lower redshift galaxies. They included CIRSIC profile, or the CIRSIC index, and they didn't have these MID statistics because they weren't developed for 6 more years. So what do we find when we do a principal component analysis? Well, principal component analysis tells us which of the statistics are important and kind of to what level. So principal component 1 tells us which are the most important and for characterizing the data, and we see that this is also color coded by how strongly the numbers are correlated or anti-correlated. So a bluer number means that it's really strong in that principal component. So like asymmetry is really strong, and red is also really strong. But the colors don't really matter. It's just that when you compare 2 colors in the same principal component, like M20 and Gini, it would show that these 2 are anti-correlated, whereas MI and D, since they're all the same color, are correlated. So now that we kind of have this principal component basis. We can project our original data onto this basis, and we kind of get a huge mass of points that it's kind of hard to determine what we're even seeing. So I decided to use a tongue twister of a word, agglomerative hierarchical clustering technique. And with this way, we came up with a bunch of different groups of data points of these galaxies. And so this would mean that they're all quite similar in their statistics. And so the next few slides I'll show really what these groups look like, or at least some of them, and what this could mean. So let's take a look first at group 0, which is a group which has the most amount of galaxies in our redshift range. And a lot of them, and like you can see, they're very compact, they're very small. And I like to compare it to this other one, group 4, which are both, they both have a strong bulge component, but the group 4 also has a lot of them have a slight disk, and they can so they have a slight disk, so they're larger than this group 0. And then there's also this kind of group 2, which kind of is in between group 0 and 4. A lot of them are, a bunch of these are really small, but then there's also some ones that have disks as well. So just to compare, to show, yeah? Oh, okay. Quantitatively, that these groups are quite different. There's group 0. This distribution shows the effective radius, and a lot of them are quite small, as we saw in the last image, compared to that group 4, where a lot of them, or they're much larger, and even they don't have any. Group 4 doesn't have any of these small galaxies that the group 0 did. Now, we also compared these groups to Sirsic index, and group 0 seemed to have a whole range of these Sirsics, so it wasn't quite that they're all compact or all disks. So I would say that the Sirsic index wasn't a great way to determine to characterize these groups. Comparing group 0, which has a whole range, and group 4, which also has a whole range, it's hard to really determine from Sirsic alone what we're looking at. So I kind of was talking about group 0 and group 4 all along, because these are the only two groups in our sample that have a sizable population of quenched galaxies. So group 0 has the most galaxies and has a sizable number of quenched galaxies. 35% of this group is quenched, compared to group 4, which has about 25% of their galaxies, but there's a lot less of them than group 0. But it's still a lot of the other groups, like really only group 2 has any kind of quenched galaxies. The other ones have really none at all. So I also wanted to, so I've been focusing on group 0 and 4, but I also want to highlight two other groups. So there's group 1, which these ones are the most asymmetric of any of the groups. Could they be, would some people classify them as clumpy disks? Probably. And compare that to the other group that's quite asymmetric, and that's group 3. But the differences between these two are kind of, you can kind of see. The group 3 ones are also very concentrated and kind of small at the same time. But what's also interesting is that the multimode statistic kind of cleanly separates these, in addition with asymmetry, cleanly separates these two groups from each other. So group 1, all of the galaxies fall in low M and high asymmetry, meaning that they only have like one bright clump. Whereas group 3 ones have higher M's, meaning they have brighter clumps, but they're less asymmetric than group 1. So what does the future have in store for pursuing more scientific results? So the next step, so instead of just having the UDS field, I'll expand this to all the CANDELS fields. we'll be covering multiple HST bands, I, V, Y, J, and H, so that we can match a rest frame wavelength to across multiple redshifts. But we'll be using the groups and principal components that were defined in this one specific redshift range to try and track these groups across multiple redshifts. And Jen will talk all a bit about this, so just stay tuned for that. Maybe we'll be able to say the probability that this galaxy was a certain classification or not. And would love to do this with simulated galaxies, so then we can really know if we could really track a galaxy moving from one group to another and how that really works. And I also would maybe use some nonlinear relations, because principal component is a linear relationship between all of these statistics, so it'd be nice to kind of see if there's any difference in the nonlinear relations. So in summary, we grouped galaxies using, in a different way other than just traditional spiral ellipticals and irregulars. We used principal component analysis, and what we find is this, that there's group 0, which has the most amount of galaxies, also has a large spheroidal and quenched galaxy population. These are really compact and really small. There's these group 2 galaxies, which are kind of between groups 2 and 4, which were the ones that had a large bulge. Yeah, group 4 had a large bulge, but also had a disk. But they're also kind of slightly quenched. And then there was groups 1 and 3, which were the ones that were asymmetric, but they still looked pretty different. So thank you. And I wanted to say that all throughout this week, we had a bunch of people who had very interesting names for their and acronyms. So I tried to come up with some of my own, but I kind of failed. So I thought Pac-Man, P for maybe principal component, but I couldn't figure the other letters. And then maybe Raj, morphology, something, galaxies, but that didn't really work either. So if you have any ideas, I would love to hear it. Thank you.
All right, questions? Joel.
Just a quick comment. Your, especially MID statistics, seem to be very interested in bright regions, their location, their relative brightness, etc. And in many cases, these will be clumps, although our official definition of clumps excludes the center. So as we get clump statistics from I Ching Guo, it's going to be very interesting to now continue this comparison between your PCA groups and the clumps, as you did, for example, with CIRSIC, because I think that there's a lot of corresponding information there.
Mm-hmm. Yeah, I think that's really interesting. We were even talking with Yi-Chang about doing something like that.
Also on the simulations.
Mm-hmm.
Any other questions? Yes, Peter.
Just a quick one. Did you try taking the group 4 galaxies and shrinking them, in other words, involving them with the TSF for the small galaxies and making sure that they didn't end up in group 0?
No, we didn't do anything like that yet, but yeah.